Hello everyone, this is Professor Keen. I want to say a few things about the lab that you're doing this week. This is the Centripetal Force Laboratory, which is exercise 24.4. The Centripetal Force Lab, which is a student's guide, volume 2, exercise 24.4. I have 3 videos posted that show data collection, and I just want to say a few things about how you're going to be carrying out the analysis. Essentially what you're going to be doing is you have 3 data points. You only need 2 of the data points actually, but for each of the data points what you have is an object that's swinging around a central point. So here's our object, and there's a spring attaching it to a central point. And here's the other object, well, the same object swinging on a different radius. And so what you're going to be doing is comparing different features of these rotating objects. So in each case, you have a centripetal force. I'm going to call this force centripetal 1. This is case 1. And this is centripetal force 2. And these forces that are holding them in orbit are you have the measurement of those forces. We measured how much force it took to stretch the spring by a certain amount, and so you have these centripetal forces, okay? In addition, we timed how long it takes to get around 50 times, so from that you can figure out the time of one orbit for case 1, and you can also find the time of one orbit for case 2, okay? And from that information, and also you know the radius of the orbit. I think I told you what the radius was in case 1, and you have the radius of the orbit in case 2. From that radius, you can find the circumference, of course, and from the time, you can obtain the velocity or the speed at which this thing was moving in case 1 and the speed that it's moving in case 2. And what you're essentially going to be doing, your goal is going to be to verify or explore corollaries 1, 2, 6, and 9, which are on page 291. Page 291. Now, some of Newton's language you're probably a little bit unfamiliar with, so let me just explain. So, for instance, in Corollary 1, he states that the centripetal forces are in a ratio compounded of the duplicate ratio of the velocities directly and the simple ratio of the radii inversely. That sounds kind of confusing, but it's actually really straightforward. So he says the centripetal forces, when you compare these two rotating objects, the centripetal forces are in the ratio, okay, so if you compare the centripetal forces, they're in the duplicate ratio of the velocities directly. A duplicate ratio is the velocity squared. So the duplicate ratio of the velocities directly, so that means directly proportional to the square of the velocities, and the simple ratio of the radii inversely. That means to the first power, the simple ratio of the radii inversely. So it's R2 over R1, the inverse ratio of the radii. So that's the duplicate, or the simple means what power, second or first, and directly means it's directly proportional to, and inversely means inversely proportional to. So I think in my notes I mentioned this should go as V1 squared over R1 over V2 squared over R2. So you're basically trying to determine this is the same as this if you look at it more carefully. So you're trying to see if, in fact, the ratio of the forces required to hold these in orbit goes as this ratio. So you're going to have to check whether or not that's true. Corollary 2 is the same kind of thing. He mentions that the forces should go as the compounded of the ratio of the radii directly, that is, it should go as the ratio of the radii directly, and the duplicate ratio of the periodic times inversely. Okay, so the duplicate ratio of the periodic times inversely. So it's inversely as the duplicate ratio of the periodic times, right? So this is what you are going to be exploring. Is that, in fact, the case? All right? That's Corollary 1 and Corollary 2. Corollary 6 is a little bit different. As I mentioned in my notes, it says something along these lines. If it's fundamentally different than these two. It says if you have a situation where T1 is to T2 in the same ratio as R1 is to R2, to the 3/2, he says a sesquiplicate power, then we can conclude that the ratio of the forces, he says, if the periodic times are in the sesquiplicate ratio of the radii, the centripetal forces will be in the duplicate ratio of the radii inversely. That is, should go as R2 over R1, so inversely in the duplicate ratio. So it's an if-then statement. So you'll need to check whether this is true, and if this is true, then this should be true. On the contrary, if this is not true, then this should not be true. Okay? And finally, corollary 9, what you're going to be doing there is you do not need to use two separate orbits. You can use one of the orbits to do this. And what this one, you might remember from the notes, I go through this in more detail in the notes, it makes a claim about if an object is orbiting, it's going to go in some time interval, it's going to be going through some arc length, right? So this would be the arc length that the object is going to go through. It's going to start out at one moment here and end at another moment here. And let me see, let me put a few lines in here. I'll put this line here. That's the diameter of this orbit. That's the diameter. And if we put another line over like this, this right here, this segment here, that would be the distance this object would fall fall toward the center if you were to suddenly stop it from orbiting, if the spring force, whatever force this is, simply accelerates it inward, it's going to fall with some distance, remember, and if it's a constant acceleration, you can use 1/2 at squared. The acceleration you can get from the force and the mass, so you can figure out this distance. You can also figure out this arc length during you'll pick some arbitrary time interval delta t, or some interval delta t. During that time, it should fall some distance d, or if it's orbiting, it should move through some arc length right there. And what he claims is that the arc length is the mean proportion of little d and big D. In other words, little d is to the arc length as the arc length is to big D. So in other words, this arc length is a mean proportion of the distance it would have fallen in the presence of this force to the diameter of the sphere. So you're going to be checking whether or not this is the case. Okay, best wishes. If you have any problems, of course, you can attend my Zoom office hours, and hope the lab goes well.